Hi, I'm Shravan. I'm a grad student at UMD. Today I'm presenting Hyperproofs, the first vector commitment that is both efficiently aggregatable and maintainable. This is a joint work with Alexander Chepurnoy, Papamanthou, Alin, Tomescu, and Yupeng, Zhang. Yeah, so vector commitment, in short for VC, allows the prover to commit to an ordered sequence of values. And given the vector, the prover can open any position in the vector with a short proof, and any verifier can check, given the commitment and the proof, to see if the proof checks out. A key security property which we want from a vector commitment is it has to be position binding, meaning let's say the prover has committed to message m at position I, then the prover should not be able to come up with some other message m prime that is also accepted by the verifier under the same commitment. A quintessential example of a vector commitment is a Merkle tree. Vector commitments are useful in verifiable storage, stateless blockchains, and many applications continue to emerge. So prior work can be categorized into two categories. In the first category, we have vector commitment schemes that have constant size proof. They are easy to aggregate. They are unfortunately hard to maintain. So when I mean by maintain, it takes, you cannot update all proofs in sublinear time. And the other class of vector commitments, we have logn sized proofs. They are not efficiently aggregatable. However, they are easy to maintain. You can quickly update all proofs in logn time. A good example of this is a Merkle tree, one more. So an obvious solution that comes up is, can we use SNARKs to aggregate Merkle proofs? But unfortunately, this is computationally intensive and may not be efficient in practice. For instance, it takes millions and millions of constraints to aggregate Merkle proofs using SNARKs, and it also has large memory overhead. So that brings us to the question which we ask: can we build a vector commitment scheme that is efficiently aggregatable and maintainable? So why do we care about these two properties? So first, efficiently aggregatable and maintainable vector commitment is an open problem, and the only known solutions which we have are fairly inefficient. And moreover, aggregatable and maintainable VCs have applications in stateless blockchains, so that it's useful in that setting. So our contributions are: we present the first aggregatable and efficiently maintainable vector commitment. Our aggregation is 10x to 41x faster than Merkle tree-based alternatives. And in fact, it takes 2 minutes to aggregate in our scheme, whereas it could take anywhere between 20 minutes to 1.4 hours in Merkle tree-based approaches, depending on the choice of the hash function. And we can update all proofs in 2.6 milliseconds. And our proofs are really small. It just takes 1.44 kibibytes. Unfortunately, this comes with a slightly larger aggregated proof size, which is 52 kilobytes. And we need linear-sized trusted public parameters to do this. So jumping into the details of our construction, so what we do is, like, we represent the vector, say, A0 to A7 as a multilinear extension polynomial. So it's a multivariate polynomial. So what we do is, so we take A0 from the vector, multiply it by 1 minus x3 times 1 minus x2 times 1 minus x1. We call this as the selected polynomial. So if you plug in, say, x equal to 0, the binary representation of 0, when you substitute 0 in these variables, you can get A0 out of this. So you can, again, do this for A1. You take A1 and multiply it with 1 minus x3 times 1 minus x2 times x1. So if you plug in the binary values of 1, you can see that you can get A1, while you can still get A0 when you plug in 0. So we can continue to do this for all other values in the vector. And build a polynomial, multivariate polynomial, which is a multilinear extension of the vector A. So to generalize, all you have to do is, if you want to get an index AI out of our polynomial, all you have to do is plug in the binary decomposition of those values, and you can get AI out of this. So given a multilinear polynomial, a multilinear extension F, we can commit to this polynomial using PST commitments. It was proposed by Papamanthou, Shru, and Tamasya. So all you have to do to get a PST commitment of S is you need to raise G raised to F of S3, S2, S1, where S3, S2, S1 are trapdoors. But you do have public parameters that has G raised to S1, G raised to S2, and so on. So you can efficiently compute this commitment. A key property of PST commitments are they are homomorphic in nature. PST of f times PST of f prime, you can get, it's the PST of f plus f prime. So we do use the homomorphism property extensively to update proofs and update the digest. So in hyperproofs, a commitment to a vector A is simply the PST commitment to the polynomial f. So we also present a data structure called as multilinear tree in this work. Before I jump into how it works, I'm going to begin with a toy version of the multilinear tree, and which will help us understand how the multilinear tree in fact works. So as you recall, f is the multilinear extension of the vector A. What we do is, you can first decompose it into two halves, f0 and f1, where f0 is the multilinear extension of the left half, and f1 is the multilinear extension of the right half. Now you can further divide f0 into the multilinear, its right half and the left half. So you get f sub 0, 0, which is the left half of the f0, and f sub 0, 1 is the right half of the f0. You can do this all the way until the bottom of the tree, where when you just have the constant a0 and a1 remaining. Similarly, you can do this for other nodes in the tree, and you can build this toy tree first. So getting into the details of how we construct multilinear tree. So what we do is we take f1, and which is the right sibling, and subtract it by its left sibling. So f1 minus f0, we put it in a node in our multilinear tree. Then in the next level, we take f sub 0, 1 and subtract it by f sub 0, 0 and put it in the next level of the multilinear tree. I can do this for the other sibling, where I just take the right sibling and subtract it by the left sibling, and I keep doing this for all the values in this toy tree which I have. And lastly, we add the vector values in the base layer for technical reasons. Yeah. So the tree which we have constructed from this toy tree by subtracting the right sibling by left sibling, that's the multilinear tree. This is how we construct this multilinear tree. So in the next slide, I'm going to get rid of this toy tree and just show you guys show you guys the multilinear tree in its all glory. So we have this multilinear tree, and each node is going to be an MLE polynomial, which is the difference of its corresponding siblings. Rather than just storing polynomials in each node, we commit to it using PST commitments. So PST commitments are a constant size, and it just takes n log n time to compute this tree. However, doing this naively would take n squared time. So jumping into how a proof and hyperproofs work, it's simply the path from the leaf to all the way until the root. So so if you want to prove A5, you just have to traverse the path from the leaf all the way until the root to those values make up the proof. Our proof is log n size, and verification also takes log n time. As you might have guessed, checking this proof involves a certain padding equation, and that corresponds to the underlying multilinear extension polynomial f. Yeah, jumping into the maintainability of our vector commitment, we rely on two key properties. One is the homomorphism of the PST commitments and the homomorphism of the multilinear tree. And say a value A5 changes in the leaf, we correspondingly update the correction factor, like in this case PST of delta, and we multiply with the value in that level. In the level above that, we multiply it with PST of delta times x1, and the layer above that is PST of x1, 1 minus x2 times 1 minus x1. So recall that 1 minus x2 times 1 minus x2 times x1 is actually the selector polynomial. The selector polynomial would depend on the index which you are updating. So if you're updating A7, and then the values with which we multiply the multilinear tree would change correspondingly. Yeah, all we have to do is just traverse the path from leaf to the root. So it just takes log n time to update all proofs and hyperproofs. Yeah, to aggregate proofs, essentially we need checking a proof involves checking this padding equation. So we plug in the proof values W3, W2, W1, and we also plug in the digest to the vector and the value A5. And we also have G raised to S3 minus 1 and G raised to S2 and so on. These are the PST commitments to the selector values which we have. So if this padding equation checks out, we do know that this proof is in fact valid. So checking a proof, it's synonymous to seeing that it's an inner product between the proof and the selectors is one way to see how the pairing equations work. So in a more general sense, we have a tree of height L, and we want to check if this pairing equation holds good. When we have k such proofs, we have to check all of these equations hold simultaneously. So we need to prove knowledge of WIs, IJs, we use inner product arguments by Bunz et al. To aggregate proofs in our system. So all we have to do is take the individual proofs, get the random linear combinations of it, and run it through inner product arguments to get the aggregated proof. So aggregated proof is a log of k times L, where k is the number of proofs and L is the height of the tree. And aggregation time is O of KL. Quick run through of our benchmarks. So our aggregation time is 10x faster than the Merkle tree based alternative. So here we use Poisson hash function. It's a SNARK-friendly hash function, but it lacks enough cryptanalysis to use it right away. And in the paper, we also present numbers with Peterson hash values as well. So yeah, our aggregation is 10x faster. On the other hand, our verification and proof sizes performs bad when compared to the Merkle tree alternatives. However, when we do macro benchmarks, the end-to-end performance still gets carried over. Our block proposal is still 10x faster, but on the other hand, validation time and proof maintenance is slow. It's fine, but still the end-to-end performance, we still come out better than the Merkle tree-based alternative. In conclusion, our VC scheme is the first efficiently aggregatable, maintainable, and we also present a property called unstealability, which I couldn't get touched today, but it incentivizes proof computation. And yeah, we have superior performance than Merkle tree approaches. And one way to see it is as an algebraic alternative for Merkle tree. So with that, I'll stop and take questions.